Thermodynamic processes. So for the next, I'm trying to think, this extends to the whole rest of the lecture. This is going to extend for a majority of the rest of the lecture, if not the whole rest of the lecture, is this kind of device. So what this is a gas chamber with a controllable temperature, a movable piston. It can be moved, it can be fixed, which you can use to change the volume, a pressure gauge, and an external gas tank, so you can add more gas, whatever you need to do. So this is the book's picture. It's like, more realistic because it shows in detail about everything that's going on. This is sort of my little sketch, kind of simplifying everything. So you've got a contained gas. There's a thermal reservoir where you can add heat or you can cool off the gas down here, and then a piston. So you can move the piston up, or you can put a little lock on this and keep the piston from moving up or down. That's the basics of what we're talking about. It's a closed system, so presumably the gas isn't able to escape. So a thermodynamic process is a change in pressure, volume, and or temperature, and as we've seen that if one changes, it's going to affect other terms. So last week we talked in terms of energy. Heat transfer is a form of energy. And so if you've got this thermal reservoir, we know there's going to be heat transfer either to the gas or from the gas. So energy is going on here. Work can be done by the system. So if you heat up the gas and you allow this piston to move on its own, the gas is going to want to expand, and so it's going to force that piston to go up. So that would be work done by the system. You can also do work on the system if you manually push this piston down or up. And this is not really the same thing, but it's kind of a cool little thing I made in college, where you can kind of see the difference between work done on a gas versus work done by a gas. So this was just a little machining project I did where you're trying to get the diameter of this to be as close to the inner diameter of that as possible, so that they're really hard to push together. And when you do that, then you're having to really work hard to force that gas to allow the piston to go in. And there is a gap, so the gas is able to leave this, but you can see the difference between, I'm forcing it closed, and then if I release it, then the gas is going to push back, So it's like a piston, basically. So we assume any changes that happen to this system are happening slowly, so that the gas, all parts of the gas are all in thermal equilibrium with each other. And since we talked about work, then let's do a little bit of remembering about what our definition of work was back from 221. I don't know if we made too much use of this in 222. But in 221, we said that work is equal to force dotted with a distance, right? So usually it was just force times distance because we were dealing with one-dimensional problems. So if we want to know a little bit of work done to move that piston a little bit of distance, then we've got the same formula. And then force, I replaced force with pressure times area. So that actually comes from another definition of pressure that we haven't used up until this point. So unless you guys had fluids, some of you have had fluids with me and some of you haven't. So from fluids, we learned that another definition of pressure is force over area. And that came about, if you consider a cube that's underwater, then the water is going to push on all sides of that cube with equal force. And so that's exactly where pressure comes from, is, the bottom is going to have more force on it than the top because the water gets more dense the further you go down. So that's directly related to the surface area that that force is encountering, how much pressure is on that box. So anyway, that's how I replace force with pressure times area. And then if you combine area with a little bit of distance traveled, so we're talking again about a piston. So if I force this piston to move up some distance ds, then and then this plate here has a surface area of A, then what is the change in volume that I've shaded there in black? So the change in volume would be, I call it ds, I guess, since I have or I call it dv because I've got ds there. So what would be the little bit of change in volume here? Like, how would you calculate the volume of this shape? The surface area of the top times the height. Yeah, the height we call ds. So that's what I did. I just replaced the area times the little bit of distance the piston moved with a little bit of volume change. All right, so now we have a relationship that says work, or a little bit of work done on the piston, is equal to the pressure of the gas times how much volume changed. And then we add our integral sign, and we can see that work defined would be the change in volume. Those are the limits, and then it's just pressure times dV. All right. So that's going to come up. Let's see, where's a good place to put that? I guess I'll put it here. So we are going to use this equation for certain instances in the future. Sometimes we can simplify this to just pressure times delta V. So the simplified version of this work is just pressure times delta V. But we can't always use this simplification. Okay. So we'll talk about instances when that simplification works and instances when we have to actually go through the integral. All right. So how we visualize some kind of thermodynamic process happening is with a PV diagram. So we know that pressure and volume and temperature can change, and sometimes you'll see a PT diagram, pressure as a function of temperature. Most often though, we just see pressure as a function of volume change, PV diagrams. So that's how we're going to visualize these thermodynamic processes. And then the area under the curve, whatever line you've got on your PV diagram would give you work. That directly comes out of our relationship we just derived. So that's really handy. All right, so I'm going to qualitatively talk about some thermodynamic processes. So this is a PV diagram here, and let's say you've got your gas up here in this state 1, where you've got high pressure and low volume, and that can get to state 2 a number of different ways. So state 2, you've got low pressure and high volume, right? So that's saying it starts out, it's got high pressure and low volume. So I've compressed it, I can feel there's a lot of pressure in there. State 2, I've increased the volume, then my pressure decreases. So there's a number of ways to get from point A to point B, or point 1 to point 2 in this case. We can keep the pressure constant and increase the volume, and then keep the volume constant and decrease the pressure. We can do vice versa, or we can follow this path where we change the pressure and volume simultaneously. And we'll walk through those 3 examples. So The first one, example one, is where we change the pressure and volume simultaneously. So we follow this curve. The mechanism for that happening would be if we physically, manually pulled that piston upward, then you could get this kind of curve. And then we calculate the work would be all the area under this curve. The arrow direction is pointing to the right, so that tells us that the work is positive. Yeah. Okay. Now example 2 is a 2-step process. So I kind of already said this. The first step, you increase the volume while you keep the pressure constant. And then step 2 is you decrease the pressure while you keep the volume constant. And so how are you doing that? You're doing that if you kept the volume constant but you wanted to decrease the pressure of the gas, you'd have to cool the gas off in some way. So we are doing some changing of temperature here, but that's not really well represented on the pressure versus volume graph. So what is actually happening here? For the first step, if you heat the gas and allow the piston to rise on its own, that'll keep the pressure constant. So the pressure only changes if you force the piston yourself. But if you allow the piston to rise on its own, then the pressure stays constant. And then once it's risen up to the desired volume, then you fix that piston so it can't move anymore and cool the gas down. That's going to decrease the pressure while keeping the volume constant. So here we see the area under the curve is much bigger, so this takes more work. It's positive work because the arrow from 1 to 3 is to the right. Okay, and then the last means of going to through that process would be to go this route, down and then over. So the mechanism for how we can do this is we first, we fix the volume, we remove the heat from the gas. Oh no, sorry, I have this backwards. We would have to allow we'd have to fix the piston for step 1 because the volume is constant. Fix the piston and cool the gas down. That would lower the pressure. And then once it's at the desired pressure, then we can allow the piston to slide again and heat the gas up. And that would keep the pressure constant while allowing the volume to change. So let me change this here. Okay, that's better. All right, so this example we see the work for this process is much, much smaller. It's the smallest of the cases. But it's also positive work. So just because it takes 2 steps to do something doesn't mean that we're using more energy to do that. So this step, or this case, we use the least amount of energy to achieve our desired goal. And so what we've seen, most definitely work was path dependent, meaning that the path we chose changed how much work was done. And we'll talk about why this is true, but the heat is also path dependent. So the amount of heat that enters or leaves that gas is going to depend on which path we took as well. So that's something we're going to keep talking about again and again and again. But write it down now so you have it for later. But so Q is heat and work are path dependent. All right. Did I explain that term well enough so that you guys understand what it means to be path dependent? All right.
You mean your diagram path?
Yeah, exactly. So we got different values for work if we took a different route. That's exactly what it means. All right, so some questions now. This is question 19.3. This PV diagram shows two ways to take a system from state A to state C via state B or via state D. For which path is work greater than 0? All right, has everybody processed it, or is it, anybody have any questions about what they're asking us? Let me just gauge whether you guys know what we're doing. So where are we starting? Where's the gas starting? A, and where is it going? To C, okay. And so we can go this way, or we can go this way. Okay, so who thinks that path ABC has positive work only? 2 votes. Who thinks that path ADC has positive work only? Who thinks that both paths have positive work? 1, 2, 3, 4, 5, 6, 7, 8. Who thinks neither path has positive work? 1 vote. And who thinks that the answer depends on what the system is made of? Nobody. Okay. So what did we say determines whether work is positive or negative?
The right is positive.
The arrow, yeah, the direction of the arrow. So the only thing that determines whether work is positive is if the arrow is going to the right. If it's negative, the arrow would point to the left. So if we were going from state D to state B, then it would be negative work. And the work would be defined by the area under this curve. So for this case, we're going from here to here, and both of the paths that have area under them, that would be from B to C or from A to D, those arrows are going to the right, therefore work is positive. Okay, any questions on this one?
So in this case, ADC would have less work?
Yeah, less work than ABC. Good. Okay, so continuing on. A thermodynamic cycle is when we take a gas from some initial state through a series of thermodynamic processes and we end up back where it started at its initial state. So here's a little example of a PV diagram where you could take it up and down this curve and then back again, and you'd end up back where it started. So if you have a closed loop, calling this a loop even though it's not circular, that's a thermodynamic cycle. And then the work done would just be the area enclosed by that circle, or loop. Okay, the first law of thermodynamics. This just says that heat and work are path dependent, which we've already said, but the change in internal energy of the system is path independent. Okay, so that's important. We'll add that to our board over here. So delta U, and that equation tells us that delta U is equal to Q minus W is path independent. Okay, so that means that if we go back to those 3 examples that we did earlier, that the change in internal energy, the delta U, would be the same for example 1, example 2, and example 3. So that kind of tells you that for each of those examples, we know that example 1, or example 2 had the most work. Example 2 had the most work. Example 3 had the least work. But this says that the change in internal energy, because they all went from the same initial state to the same final state, would be the same for all of them. So delta U is the same for all of them. So what would that tell us about the heat for example 2 and example 3? So if this one had the most work, this would have the least heat, yeah. And then example 3 would have the most heat. I know that's very qualitative, but it gets you at least thinking about these ideas. And then whether delta U is positive or negative is just actually looking at the mechanism itself. So if you actually had to add heat to a gas, then you have positive delta U. And if energy is lost due to work done by the system, so that means the piston rises of its own accord or falls of its own accord, then you're losing, then you have negative internal energy. Or if you've got some kind of heat loss. But of course, if the gas rises of its own accord, it's going to cool itself off that way. So it's similar to, or it's counter to this one. Positive delta U, heat added to the system. Negative delta U, essentially the heat's going to be lost from the system. So basically we got a whole bunch more terminology. So does anybody have any questions about these terms before we move on? Yeah, Leland?
What's the internal energy? What's like the units, or is there?
It's joules.
Okay.
Yeah, and just like heat has units of joules, work has units of joules, so they're all different words for energy. They're all forms of energy, yeah. Okay, here's your question 9.1 from your worksheet. A system can be taken from state A to state B along any of the 3 paths shown in the PV diagram. If state B has greater internal energy than state A, along which path is the absolute value Q of the heat transfer the greatest? All right, has everybody made their choice? Who thinks the answer is A, path 1? 2 votes. Who thinks it's, 3 votes. Who thinks it's B, path 2? Who thinks it's C, path 3? 1, 2, 3, 4, 5, 6, 7. Who thinks it's D? Q is the same for all paths. Who thinks it's E, not enough information? All right, so 7 people voted for C, path 3. So somebody voted for path 3. Tell me why.
Looking for the one that has the least amount of work.
The least amount of work, why?
Because that would mean that it has the most amount of heat.
The most amount of heat, all right.
What was that equation?
That one looks really squirrely.
Because it's squirrel, so Grant voted for 3 because it's squirrely.
It's not doing a lot of work, so.
He's slacking off, he's having too much fun. What Leland said is correct about path 3. Yeah, so that one has the least area under it, so the work would be smallest. And we see that in order to balance this equation, then we're looking for the Q that's the greatest. So that would be path 3. The only thing that there's like information that we don't really need to think too hard about, and that's that they tell us that state B has a greater internal energy than state A. So that just tells us that the delta U for this process is positive. Yeah, so if you've got positive delta U, and we see all those arrows are pointing to the right, so we have positive work, then our Q has to be positive. But of course, then they said absolute value of Q, so then that doesn't really matter. But yes, so the C is the correct answer. Are there any questions about this one? Okay. 19.2, same picture. Now we're asked if state B has greater internal energy than state A, along which path is there a net flow of heat out of the system? All right, anybody need more time? Nope. Okay, who thinks it's A? Who thinks it's one vote? Who thinks it's B? Who thinks it's C? Who thinks it's D? One vote. Who thinks it's E? 1, 2, 3 votes. And a lot of people who didn't vote, so a lot of people are confused, which is fine. We're getting into the murky here. So this kind of, so since there was no consensus, general consensus, the correct answer is E. There isn't a path where heat is flowing out of the system. And so that goes back to what we said down here at the end here. So positive delta U, heat is added to the system. Negative delta U, heat is lost, or energy is lost due to work done by the system. So the negative delta U would mean heat is lost from the system. And since they tell us that from state A to B, or state B has greater internal energy, then we know we'd have a positive delta U. So a positive delta U means that heat is added to the system, not taken away from the system, for all of these cases, since the arrows are all going from A to B. Any questions on this? Did that clear it up for people, or are people still unsure about why the answer is E?
So I have a quick question. If the work, let's say, there was negative work,
Okay.
but it still had higher internal energy. Let's say.
Okay, sure. If you went from B to A, then you'd have negative work.
Well, let's move the kind of close those, instead of having a B here and A here, do it something more like this.
Okay. Let's see if I can do what you're saying to do, like this. No.
No.
Like this.
Yes. And you still have negative work.
And so this would be the path.
Yeah, I guess that's what I'm.
And this is A and this is B,
we're
or
going from B to A.
oh, we're going. And where is there higher internal
A would
energy?
have more internal energy.
Okay, I'm just going to do A to B.
That's fine.
Yeah, because then that follows with this. So then we have delta U is positive,
Yeah.
positive delta U, and a negative work
Yeah.
because the area, well, because the arrow's to the left. So positive delta U is Q minus W. This is positive. This number is negative. So negative plus a negative would be positive. Can this be, let's see, because this could be like if we have just numbers in here, let's say this is 10 and this is, so this would be a negative times a negative, say negative 5. This could be 5, and that would be a positive Q.
Okay.
Is there an example, but is there an example we can think of where this could be a negative number? Because we could have this be like negative 10, and if you added to that
That'd be 20.
negative 20, you'd still end up with positive 10. Yeah, so your example, we wouldn't have enough information. Yeah, because a Q could be positive or negative. It's tricky, and maybe this is a good way to go about it. For this case, we can throw in numbers, and you should always get Q would end up being positive, so there's no heat out of the system. Does anyone want to see, like with numbers, the actual problem we just solved? Nobody? Okay. All right. Okay. So the next thing we're going to do is we're going to walk through 4 thermodynamic processes. So we've qualitatively showed